Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and/or questions, drop them in the comment section below or write to us info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Hello everyone. Thank you very much for joining us for today's Oxygen Talk, which is brought to you by the Oxygen Alliance. My name is Foster Sentala. I'm a biomedical engineer with the Oxygen Alliance, and I'll be your host today. I'm hosting this call from Lilongwe, Malawi. So the Oxygen Talk is a virtual meeting that the Oxygen Alliance hosts once a month on a Thursday from 2 p.m. to 3 p.m. Central African Time, where we discuss various topics related to oxygen equipment. Today, we are having biomedical engineers from the Open O2 who will share invaluable knowledge on medical oxygen analyzers and monitoring devices. At the end of the presentation, there will be time for questions and/or comments, and so you can take notes so that I give you a chance to ask. Once again, my name is Foster, and I would also like to know where you're joining us from. So you can type your location in the chat, and also you can include your email so that we add you to our emailing list. This will help us to notify you whenever we have oxygen talks like this one. So without taking much time, I will now hand over the stage to Lloyd Kayembe, who will introduce the whole team and also kickstart the presentation. Over to you, Lloyd.
Thank you so much, Foster Sentara. My name is Lloyd Kayembe. I'm a biomedical engineer for the Oxygen Alliance. Today I'm with my colleagues from Open O2, Chimwemwe TS and Elizabeth Ntabalapa. So as pointed out by the host, indeed, today we're going to talk about oxygen analyzers and monitoring devices. In this presentation, we're going to introduce to you oxygen analyzers and monitoring devices. We're going to discuss as to why oxygen analyzers are important. We're going to discuss some of the technologies that the oxygen sensors in the oxygen analyzers use and how to calibrate different types of oxygen analyzers. We're going to discuss the common faults and problems associated with each type of oxygen analyzer and how to troubleshoot some of the common issues. We're also going to share you oxygen monitoring device technologies, and we're also going to share you how to properly use oxygen analyzers. Lastly, we're going to share you some of the innovations in oxygen sensors. So moving on, so what are oxygen analyzers? So oxygen analyzers are devices that measure the concentration of oxygen in a gas mixture. They are very important devices and see many applications in industries and healthcare facilities. In the industry sector, they are used to monitor and control the oxygen level in processes such as combustion, welding, food packaging, and more. For example, in combustion processes, maintaining the correct oxygen level is very crucial for efficiency and safety. In the healthcare sector, oxygen analyzers are used to ensure that patients are receiving the correct concentration of oxygen, so particularly those who require supplemental oxygen. So we shall explore in more details the crucial significance of oxygen analyzers in the medical field. So just to take note, the crucial component of oxygen analyzer device is the oxygen sensor inside. This oxygen sensor can be integrated with oxygen equipment and different machines that provide some sort of oxygen therapy. So these examples are anesthesia machines and oxygen concentrators. So just keep in mind that oxygen analyzers have a wide application, but today we are going to focus on oxygen analyzers for medical applications. Yeah, so why do we need to talk about oxygen analyzers? So imagine giving a wrong medicine to a patient. For sure, this would completely compromise patient safety and lead to potential life-threatening conditions. So this is just the same with oxygen. It is important to verify that correct concentration is given to a patient. Actually, medical grade oxygen has been classified as a drug and needs to be prescribed by a qualified healthcare professional. So oxygen analyzers will help you determine the oxygen percentage of your source and make sure that the oxygen is safe to be delivered to the patient, ensuring patient safety. So secondly, during surgery and anesthesia administration, it is important that accurate oxygen levels are maintained. So the oxygen analyzers in the machine will help the anesthetist ensure that the patient is receiving proper oxygen concentration to prevent complications. The third point is about quality assurance. Oxygen analyzers will help ensure that the machine or the source of the oxygen that you have is meeting the specified standards, so as to ensure the effectiveness of oxygen therapy and treatments. So oxygen analyzers will also help to assess if oxygen concentrators are working in the right condition. So oxygen analyzers also help in record keeping. So basically, the data that is taken using oxygen analyzers will help in making informed decisions. So they basically help to track the performance of different oxygen therapy machines, like the oxygen concentrators, over their lifetime. So this will help make the right decisions in the procurement processes and the maintenance plans, as one will be able to see the performance history of different devices. So now I'm going to invite my colleague, Chimwemwe TS. He will take us through different technologies behind these oxygen analyzers. So Chimwemwe TS, I give you the floor.
All right, thank you so much, Rohit, for that. So there are three main types of medical oxygen sensors. We have ultrasonic oxygen sensor, electromechanical oxygen sensor, and paramagnetic oxygen sensor. In the next few slides, we will learn how each of these three types of medical oxygen sensors work. That is the ultrasonic, electrochemical, and the paramagnetic. We'll also break down how each of them operates, so it's easier for us to understand. So moving on, I'll first talk about the ultrasonic oxygen sensor. The ultrasonic oxygen sensor consists of four main parts or components. The first, it has the inlet in the outlet ports that allows the gas to flow through. You can see that in the graphics to your right. Then there are ultrasonic transducers located at the either end of the sensor. These transducers send out and receive ultrasonic sound waves. So in some sensors, there is a separate part for sending and another for receiving, while in others, they take turns in doing both jobs. So next is the electronic circuit. This circuit is like the brain for the sensor. It takes in the signal from the ultrasonic transducer and then uses them to figure out how much oxygen is in the gas. So these sensors come with a protective housing. This housing keeps the sensor safe from the environment, and it is also where the sensor is attached to its place. So another thing that I should mention here is that some ultrasonic oxygen sensors have an extra part called a thermistor or a temperature sensor. This temperature sensor measures how cold or hot the gas is, so in adjusting the oxygen leading to make sure it's accurate, even when the temperature changes. So I'll talk about how the temperature changes affect the leading concentration that is shown on the oxygen analyzer, which uses this type of ultrasonic oxygen sensor. So the ultrasonic oxygen sensor sensing is based mainly on the relationship between the speed of sound in gas, which is proportional to its molecular weight. So this principle is particularly useful for measuring the concentration of two gases in a mixture, like oxygen and nitrogen. So we all know that air is composed mainly of oxygen, which is 21%, and nitrogen, which is about 78%, or which is 78%. So at 20 degrees Celsius and 1 atm pressure of sun, the speed of sound in pure oxygen is approximately 330 meters per second, while the speed of sound in nitrogen is approximately 354 meters per second. So when we know the molecular weights of these gases, we can determine the volume percentages of each gas in the mixture by analyzing the speed of the sound in the mixture. So in simple terms, we can have when we have a mix of two gases, we can use the speed of sound in that mixture to figure out how much of each gas is there, as long as we know their weights. So this becomes handy, especially when dealing with gases like oxygen and nitrogen, which we already know that they are the most common, they're the ones that are mainly found in air. So moving on, we'll look at how ultrasonic oxygen sensor and ultrasonic oxygen sensors do flow measurements. So ultrasonic oxygen sensors uses the ultrasonic sound waves to measure the flow of gases, such as the gas which we are mainly focusing here, that is the oxygen. So the basic principle behind these sensors involves transmitting ultrasonic waves through the gas medium and then measuring the changes in frequency of the reflected wave to calculate the flow rate. This is done in what is called with what is called the Doppler effect. So this is I'll explain now how this works. So one of the transducers emits an ultrasonic wave, which are sound waves which are with a known frequency into the gas stream. So some sensors may use frequencies in the range of 25 kilohertz to 200 kilohertz, while others can go up to megahertz range. So if a gas is in motion, such as flowing through a pipe, the moving gas molecules cause the ultrasonic waves that are transmitted by these transducers to experience a change in frequency due to the Doppler effect. This change in frequency is proportional to the velocity of the gas. So this change is direct proportional to the flow rate of the gas. So when the gas molecules move towards the sensor, the waves are compressed, resulting in higher frequencies. So when the gas molecules move away from the sensor, the waves are stretched, resulting in lower frequencies. So the sensor detects these ultrasonic waves after the interacted gas. It measures the frequency by the received wave. But then, by this time, it can analyze the changes in the frequency between the waves. So the sensor can then calculate the frequency or the speed of the gas. With an additional information about the cross-section area of the gas, and volumetric flow rate of the gas. So this can be actually shown on the oxygen analyzer, which is using this type of sensor. So to put it simply, and an oversimplified equation is you can use flow rate is equal to K1 times the Doppler shift, which is caused by the Doppler effect, which I've just mentioned. So this K1 is a calibration constant, and it is set by the manufacturer. So as I have already said, the constant is determined by the manufacturer of the ultrasonic oxygen sensor. So it is typically determined by calibrating the sensor against the known flow rate. So this is all done at the manufacturer's end. I will next talk about ultrasonic oxygen analyzers and how the sensor aid is used to measure flow rate and also concentration of oxygen. So ultrasonic oxygen analyzers are widely used in medical equipment like anesthesia machine, ventilators, and also the oxygen analyzers, as I just said. So these devices measure oxygen concentration in the range of 21 to 95.6%. Of course, it can go above this range for some oxygen analyzers up to 100%. But for the analyzers that are typically used to measure concentration of oxygen from an oxygen concentrator, they are capped at 95.6. And typically this is done on a flow rate of from 1 to 10 liters per minute. So this will help us when you use these analyzers. It helps in ensuring patient safety and effective oxygen delivery. So most handheld analyzers offer portability for quick on-the-spot assessment for oxygen concentrators and also the anesthesia machine and the ventilators. So in addition to the inclusion of the pressure, in addition to this, there's also an inclusion of pressure monitoring capability, which further enhances the utility of these oxygen analyzers and also maintaining the safety and effectiveness in oxygen delivery. So this feature comes in handy mainly during maintenance and repair of the oxygen concentrator, just to make sure that we put back the concentrator at the pressure which is rated by the manufacturer. All right, now we'll move on to look at the common faults and problems with ultrasonic oxygen analyzers. So ultrasonic oxygen analyzers are used for measuring oxygen concentration and oxygen in various environments, be it in hospitals or industries. So of course, we've said our main emphasis on medical use. So while these analyzers are generally reliable, they can experience common faults and problems, just like any other analytical equipment. So some of these typical issues that may arise with ultrasonic analyzers include the sensor contamination. So contamination is a main issue that can cause issues in accuracy of the reading on oxygen analyzers. So the surface of the transducer can get contaminated by dust, oil, or other substances that accumulate on the sensor over time. So one thing to take note of is that ultrasonic oxygen sensors must be stored in a dust-free and a clean environment. Another thing that can cause inaccurate readings on the oxygen analyzers is temperature variation. So fluctuation in ambient temperature can affect the accuracy of the analyzer. So I alluded to this in the earlier slides. So most analyzers have temperature compensation features inside, as I showed when I was just introducing the ultrasonic oxygen sensor, that some have a temperature sensor inside. This is used to compensate for the changes in temperature, which may cause fluctuations in the oxygen concentration. But if these sensors are not functioning correctly or temperature varies beyond the compensation range, it can lead to inaccuracies. Another thing that may affect the accuracy of measurement of the oxygen using these oxygen analyzers is the vibration and mechanical shocks. So ultrasonic analyzers are a sensitive instrument, especially the transducers, since they are made up of crystals. So exposure to excessive vibration or mechanical shock can damage transducers and lead to measurement errors as well. So another thing that can cause errors or display inaccuracies on the oxygen analyzer are cables and connection issues. So faulty cables or poor connection between the analyzer and the components can lead to signal loss or interference, which can also result in inaccurate readings. While we are still here on issues affecting this ultrasonic oxygen analyzers, another factor that can affect the accuracy of reading is gas flow rate variation. So variation in gas flow rates can affect the accuracy of the analyzer's readings. So what you can do is that you should ensure that the gas flow is consistent and is within the recommended range for oxygen analyzers. If the analyzer said that it can measure from 1 to 10 liters or 1 to 20 liters, you should measure within that range. If you go above this range, you get inaccuracies in reading, because of course this will be what the oxygen concentrator is giving you, or it's because the analyzer is also only designed to work within that rated flow rate. So one other thing that commonly, which of course this may not be common, that can affect the readings on the oxygen analyzer is interference from other ultrasonic sound sources. So in hospitals, if you have issues if you have other machines that are producing ultrasound waves, you can have problems in the reading of your sensor, because this can actually interfere with what the sensor is reading inside. So identifying and mitigating such interference is very important in the medical field. So one other thing that affects the accuracy and reading is the sensor aging. So although ultrasonic oxygen sensors and analyzers can last up to 5 years without need for recalibration, the sensor can age over time and usage. So the sensor performance will degrade, leading to inaccurate readings. Moving on, I will now talk about electrochemical oxygen analyzers. So you can see in the graphics, there are two types of electrochemical oxygen analyzers. The other one is white, the other one is black, white, and blue. Made by different manufacturers. So these electrochemical oxygen analyzers work by measuring current generated by electrochemical reaction between the oxygen sensor and an electrode. So oxygen molecules diffuse through a membrane and are reduced to ions at the cathode. So what happens is the oxygen molecules will react at the cathode and produce an electrochemical reaction which generates a current. This current is direct proportion to the concentration of the oxygen analyzer. So most of these oxygen analyzers, the electrochemical oxygen analyzers, have replaceable electrochemical sensors in them. So next we'll look at these electrochemical sensors, how they are built inside, and I'll show you a closed section area of this oxygen analyzer. So moving on. As you can see to your right in the graphics, there is the electrochemical oxygen analyzer. It has 5 main parts. There's the plastic body that encapsulates the anode, the cathode, base electrolyte, and also the PCB, which houses the resistors, and also sometimes this analyzer has a thermistor, which again is used to compensate for temperature variation in measurement of oxygen concentration. So as I already mentioned, the output of this sensor is current, which is commonly measured in microamperes. This current is generated when the electrons pass through excitation process. Then they diffuse into the electrolyte solution to generate an electrical current, which is then used by the electrical circuit to show and display the oxygen leading concentration on the LCD of the oxygen analyzer, which uses this electrochemical sensor. I will next talk about the shelf life and storage for electrochemical oxygen analyzers. So storage life is a very important aspect to consider when deciding when and how to purchase electrochemical oxygen sensors, replacement for electrochemical oxygen analyzer, or when you want to buy the electrochemical oxygen sensor on itself. So these oxygen sensors work by a chemical reaction that happens inside the sensor, as just said. So when this sensor is exposed to the atmospheric gas, chemistry happens inside the sensor, which will then give out an electrical output. So this means that if the sensor is not being used, if it is exposed to air, it is still using the chemicals inside. So most of electrochemical oxygen sensors have a stated shelf life of 6 months. You may ask why 6 months. Of course, I will talk about it later in the following slide, about the lifespan of the electrochemical sensor, which is about 2 years. So if you're buying an electrochemical sensor which already has been on the shelf in a shop or in the stores for more than 6 months, that means you are drastically reducing the lifespan or the time you can reliably use this electrochemical oxygen sensor. So for better sensor life, you should only order sensors when you are ready to use them. Again, for better usage, install the sensor within 4 to 6 months from the date of manufacturing. So now I'll talk about the lifespan of the electrochemical oxygen analyzer. So a normal oxygen sensor has a service life up to 24 months, which is basically 2 years. So at 25 degrees Celsius and 60% relative humidity, the sensor can last up to the stated 2 months. So I just want to repeat here that regardless of whether or not the oxygen sensor is used, life of the sensor starts to deteriorate immediately after its manufacturing date. Next, I want to talk about the calibration of the electrochemical oxygen analyzer. So most electrochemical oxygen analyzers come with documentation on how you can calibrate. Some electrochemical oxygen analyzers or sensors come with the documentation, as already stated. So some of these allow upper end calibration, others only allow the lower end calibration, and then you have others who can allow both. You can see in the graphics, the one to your left, the black and blue, only allows calibration on the lower end, while the other you can calibrate on the upper and lower end. So for the one on the where you can calibrate for the lower and upper end, and also if you have buttons that allow adjusting the concentration, you can first start by exposing the sensor to a known source, source of oxygen with a known concentration. It can either be room air, which is at 21%, or 100% oxygen from oxygen cylinders or whatever source that's outputting 100% of oxygen. So what you do after exposing the sensor, you allow the sensor, the readings on the sensor or analyzer to stabilize. After they have stabilized, you can actually hit the calibration button. If your analyzer has buttons which allow you to increase or decrease the concentration, you can do this. So you know that at the room air has 21% of oxygen. So if you're exposed to 21% of oxygen, you reduce or increase so that the analyzer will show 21. Then you lock it. At that point, you have calibrated. You do the same. The same will work when you are calibrating at 100%. Then you have this analyzer that only work for lower end. You can just expose them to room air. When they hit 21%, you hit calibration button. It's done, and that's all. So reaching this far, I'll ask my colleague Lloyd to continue with the presentation. Thank you.
So we can define paramagnetism as a form of magnetism where certain materials are weakly attracted by a strong field. So specifically, oxygen has these paramagnetic properties. So these sensors typically measure oxygen with a maximum flow of 2 liters per minute, and they can operate between 5 to 50 degrees. So to the right is an example of a paramagnetic oxygen sensor module. So this one is a Paracube Modus digital paramagnetic oxygen sensor module. So next slide, please. So as I said earlier, the basic principle of operation is based on the paramagnetic properties of oxygen. So these sensors have different types of constructions. So some of the major constructions are the dumbbell type construction, the magnetic pressure type, and the magnetic wind type. But today we are going to focus, we are going to base our discussion of this technology on the dumbbell construction. So, so on the next slide, you see 2 images showing the internal components of a dumbbell paramagnetic oxygen sensor. So the first image is an illustration of the internal parts of the paramagnetic sensor cell, and the second image to the right is shows the physical image of the internal components of this type of sensor cell. So in the dumbbell type, the sensor contains a permanent magnet, and in between the magnets, there's an assembly of 2 nitrogen glass spheres surrounded by a feedback or compensation coils. So these spheres are mounted on a rotating suspension. So these feedback coils on the spheres also generate a magnetic field that interacts with the magnetic field of the permanent magnet, making a delicate balance of the rotating suspension. And there's also a mirror that is fixed between the sphere suspension, such that when the sphere suspension assembly rotates, the mirror also rotates. So there's also a light source that is directed onto the mirror, and the photodetector onto which the reflection of the light is directed. So the whole sensor unit is enclosed and has an outlet and an inlet. So when a stream of a gas mixture that is to be analyzed flows around this assembly, it fills the sensor cells, and because of the paramagnetic property of oxygen, its molecules tend to accumulate between the poles of the magnet. So as the oxygen is being attracted to the magnetic field, it displaces the glass spheres, causing the suspension rotation together with the mirror. So this movement causes the reflected light to move also, and then this is detected by the photocells, and the signal is then sent out to the amplifier. So then the current is then generated onto the feedback coils in order to compensate this movement of the suspension. So the current that is being generated is proportional to the oxygen concentration in the sensor cell. So the more the oxygen concentration, the more the dumbbells are reflected, and the more current needs to be sent to the coils, hence detecting higher concentration using this current. So on the next slide, I'll talk about the common problems with paramagnetic sensors. Paramagnetic oxygen sensors are affected by movement and vibrations. So since the sensors have been made to sense oxygen by the movement of the dumbbells, any movement or vibration can then affect the output of the sensor. Yeah, so that's basically how the paramagnetic sensors operates. So I will now invite Elizabeth Tabalaba to continue with the presentation. Thank you so much.
Thank you so much, Lloyd. And indeed, my name is Elizabeth Tabalaba, and I will take you through the oxygen monitoring device technologies, their components, proper use of oxygen analyzers, and also the innovations that are done here actually at Global Health in application of these oxygen sensors. So let's begin with understanding what an oxygen monitoring device is. So this is a device that measures the amount of energy in a given environment. So as explained earlier by my colleagues, these technologies are classified according to the sensors that are used. So we have the electrochemical devices that use this technology. We also have the monitoring devices that use the ultrasonic technology as well as the paramagnetic technology. And also, these systems are used in different settings, including the hospitals, laboratories, and the industrial facilities. But because we are much talking of the hospitals, that's where I'll also explain much on. So moving on, I will talk about the components of the oxygen monitoring devices. So these components vary, depend on specific system, but I'm going to talk about the oxygen sensors, alarm systems, external diagnostic ports, control systems, calibration equipment, and power supply as the common components that are included. So beginning with the oxygen sensor. So the oxygen sensors are the critical components of the oxygen monitoring device. These components, they sense and detect the concentration of oxygen in the air. So right here with me, to your left, I have this real picture of an electrochemical oxygen sensor that is used in some of the oxygen analyzers. And the next one is an ultrasonic oxygen sensor, which is either used in some of the oxygen concentrators or oxygen analyzers. Next, let's look at the alarm systems that are incorporated in these oxygen monitoring devices. So these alarm systems, they provide an alarm or alert if any oxygen concentration falls below a certain level. So according to the normal and tried oxygen concentration, which is supposed to be given to the patient, which is 82%. So if we happen that we have any concentration produced by a machine that is less than 82, then these monitoring devices, they do give out the alarms. For example, to your left, we have the picture from an oxygen concentrator showing an LEDs. This one actually is Kanta. And we're having the oxygen LED lighting up to red, which is showing that there is an alarm of low oxygen purity. And also to your right, we have the oxygen analyzer picture from an oxygen analyzer with its LED lighting up, also indicating that we are having a low alarm in the oxygen purity. Next, I am going to talk about the external diagnostic ports. So these are the systems that record data about the oxygen concentration over time. So they can be used to track changes in oxygen levels and identify trends. So this picture was taken from one of the oxygen concentrators, the M50, whereby now we have another external handheld device where we plugged in into this port, and we can get different information such as the flow rate, the temperature at which the oxygen is produced at, and also the oxygen purity. Our next component that I'll talk about the control systems. The control systems are used to regulate the oxygen concentration in a given environment. This can be manually controlled, or they can be automated. On our next slide, I'll then talk about the calibration that I mentioned earlier. So the equipment is used to calibrate the oxygen sensors to ensure that we are providing accurate readings. And it was earlier mentioned by my colleague Chimwemwe. He explained some of the processes that are done to make sure that these oxygen sensors and analyzers are calibrated. So to your left, we're having the picture from one of the electrochemical sensors. That is actually, we can see there is a button indicating that we can place there for calibration. As well as to your right, there is also that CAL indication of where you can calibrate your sensors. This is important for the safety of the end users of the oxygen gas. Next, let's look at the power supply. So for each and every oxygen monitoring device to run, they require a power source. It can be an external power supply, or we can use a battery, as we can see in our picture here that we're having an electrochemical analyzer with batteries in it. So this analyzer uses batteries for it to be operating well. After looking about all these components, now let us look at some of the application of oxygen analyzers. So in this presentation, I will talk much about two applications where we can appreciate better the application of these oxygen analyzers. So I'll talk about the oxygen sensors used in the anesthesia machines, as well as oxygen sensors that are used in oxygen concentrators. So on the anesthesia machines, the standard for basic anesthesia monitoring of the American Society of Anesthesiologists, it says that the concentration of oxygen in the patient breathing system, it should be monitored by an oxygen analyzer. That is why we're seeing these sensors being incorporated in these big machines for us to get to be monitoring the oxygen in the breathing system. To your left, we have the electrochemical oxygen sensors. Specifically, these ones are for the Menry anesthesia machines, and this one they do give the mean oxygen concentration of the breathing circuit. While to your right, we have the paramagnetic oxygen sensor. This one's for the ParaCube, and as well is this one is used to give the oxygen concentration in the breathing circuit. But we can talk good about the paramagnetic oxygen sensors to say that they have sufficiently rapid response time to measure both the inspired and end tidal levels in the breathing circuits. Moving on, I will then talk about the application of oxygen analyzers in oxygen concentrators. In as much as we have different oxygen concentrators, different brands, but here I'll just explain to you some of the two applications that are used in the Rubis oxygen concentrators, as well as the Longfian J5 oxygen concentrators. So to your right, with the use of the pointer, where we're pointing our oxygen sensing device, we can really appreciate to say the makeup of this sensor. It is exactly like how Chimwemwe mentioned it earlier, that we are having this tube with two transducers to both ends, and we have the inlet and outlet as it was also explained. And also to your right, we are having this oxygen sensor by Wintec Power for the Longfian J5 oxygen concentrator. And both of these oxygen sensors, they are using the ultrasonic principle, and they're using the ultrasonic principle to give us the oxygen utility that the machines are producing. Next, I will talk about some of the proper usage of oxygen analyzers that we need to consider as we use the oxygen analyzers. So the first thing that we need to be aware of as we use these devices is that we should be conscious about the calibration. So regularly calibrating the oxygen analyzers is important, especially we should be following the manufacturer's procedure. This helps us to be able to know to give the right oxygen purity to our patients. And the next proper usage of the oxygen analyzers is that we should practice cleanliness. We should observe cleanliness, whereby we should make sure that we're keeping our sensors clean from dirt, dust, or any other contamination. And also, we should let the warm-up time to actually let the sensors to get specified duration before taking the measurements of the oxygen concentration. Our next proper usage of oxygen analyzer that I'll talk about today is about safe handling. We should make sure that these devices are handled safely and with so much care. So we should avoid subjecting to any physical shock or extreme temperatures for us to make sure that they're working good and fine. And also for the electrochemical sensor, we need to be making sure that we're keeping it in an airtight environment, safe, since there are chemical reactions that happens. So we need to make sure that we're not exposing to the air all the time to avoid the degradation of the sensors. Next, we should regularly maintain our sensors by either replacing the sensors if they need any kind of replacements, changing the filters, and routine inspections. Lastly, we should also be able to understand what the data that is being interpreted means, because this will help us to give out the right oxygen to our patients. So, reaching this juncture, I'll just show you a little demonstration of the proper use of the oxygen analyzers in the next few slides. So this demonstration was done using the oxygen concentrator Kanta 5 liters. So before you start using the oxygen analyzers, you should have your oxygen concentrator ready, connected to the power, and then you switch it on. And then you open the flow meter to the maximum flow rate as specified by the users. So since this one is a 5 liters machine, we open the flow rate to 5 liters. So after that, we should get our oxygen analyzers. And here we use an ultrasonic oxygen analyzer. And when we switch them on, many times it's going to display to us initial oxygen concentration of the room air, which is 21%. After switching it on, and we should then make a secure connection of the oxygen analyzer to the oxygen concentrator as displayed in the next slide. Yes, so we should make sure that the connection is well secure. There should not be any kind of leakages. And after letting it stabilize, we're going to see that our oxygen analyzer is giving us the figures of the oxygen purity. For example, here in our figures, this machine is giving us the 95.6% of oxygen purity at 5 liters. And I'll also just do a quick demonstration of the electrochemical oxygen analyzer. So the same things, we are going to switch it on, and it will even start displaying the oxygen purity at 21%. And this one, we can see that we're having different thresholds, as I mentioned at some point. So we're having the lower threshold and the upper threshold. After connecting it securely to the oxygen concentrator, it is also giving us the oxygen purity at which this machine is producing the oxygen at. The next slide, please. So the steps that I showed you earlier, those were the proper things that we need to do as we're using the oxygen analyzers. But let us just look at some of the things that we may happen to do but may distort the accurate reading of oxygen purity by our oxygen analyzers. So this is an electrochemical analyzer, and from the very first picture, we're having this hole which acts as the outlet of oxygen through the analyzer. So blocking this hole, we can see that our oxygen concentration has drastically increased going above our threshold of 99%. It has reached up to 106.5%. This is because we blocked the hose which acts as the outlet, and this leads to our oxygen analyzers displaying a high alarm alert. And also, another thing that we need to be conscious of not doing will be explained in the next slide, please. Where the connection between the oxygen analyzer and the machine is secure, but then there are some kinking happening. So as we can see, the flow rate, it is showing to be 3.3, but then we open our machine to be at 5 liters. So these two demonstrations can show that in as much as we're using the oxygen analyzers, but if we're not doing them properly, if we're obstructing the hose of the outlet of the oxygen analyzer, or if there is any kind of kinking, we'll definitely have we're going to definitely have different readings which are not desired to be the outcomes of the oxygen purity produced by our machines. Next slide. I'll just explain to you some of the innovations that are done here actually at GHII in application of the oxygen sensors that we've been talking about. So to your left is an oxygen analyzer. We actually made good use of this very same knowledge that we learned from the ultrasonic sensors, and we even built our own oxygen concentrator. Our own oxygen analyzer. Yes, so this is a good representation of the innovations that we can do with these oxygen sensors. And to your right, we have this oxygen purity display. This is actually monitoring also each and every time you switch on your concentrator, the oxygen purity at which the machine is producing. And this is in connection to the data that we're getting from our machines. So these two innovations is just good representation of how best we can use these sensors, and we can even do much more apart from this. And reaching this far, I'll hand over the presentation to Lloyd Kayembe to just wrap up everything. Thank you.
Thank you so much, Elizabeth. So just a recap, we have discussed the importance of medical oxygen analyzers, and we have explored different technologies behind the oxygen sensor, that is ultrasonic, electrochemical, and paramagnetic. We have discussed the common faults and problems with oxygen analyzers. We have discussed the components of a monitoring system and the applications of oxygen sensors, and how to properly use the oxygen analyzer. And we have also shared with you innovations, that is the GHII oxygen analyzer and the 7-segment purity display. So thank you for listening. I will now hand over the stage to our host. If you have any questions or comments, you are welcome. Thank you so much. Over to you, host.
Well. A round of applause to our presenters today, biomedical engineers from the OpenO2, for a quite fascinating discussion on oxygen analyzers and monitoring devices. Now it's time for questions. Of course, we are run out of time, but firstly, I'll invite at least 3 questions from our audience. So if you have a question, you can raise your hand, and you can also type in the chat. So if you have any question, please raise your hand and I'll give you a chance to speak. I see we have 3 hands. Faith, you had raised your hand from some time. Do you have a question? After Faith, I will invite Goodluck Oboro to also ask a question. Goodluck?
Am I on? Can you hear me? I didn't start the training on time, so can I get the explanation for ultrasonic oxygen sensor? Then the second question, how long can, if a ventilator or an aesthetic machine has been installed, how long can the sensor last, or how frequent do we change or do maintenance or calibration on those machines? Thank you.
Okay, that question is taken out of. Stephen, can you also ask your question? So we take 3 questions at once, and then the engineers can attend to them.
Hello.
Yes, we can hear you. Go ahead.
Yes, okay. I had a question. Now, you see, we have been talking about the analyzer, so that is oxygen analyzers, and then I don't know if at some point we be required to calibrate the analyzer itself, or just a machine that is just capable of working for maybe a certain period of time. You need to tell us about that. And also, we have spoken about these oxygen sensors, and of course, some of them we are told that they are at times non-linear to some point. So is it possible that if the machine itself is not in use, must we replace the sensor after some time? That's the question.
All right. Thank you very much for that, Stephen. Lastly, let me take Bukua Titus.
My question is about these sensors. I don't know whether these sensors are internally in the machine or they are connected outside DC. Maybe, for example, the oxygen concentrator. And then now the question there, for example, if they are internally connected to the concentrator, assuming it has a damage or it is damaged, will there be a signal given by the concentrator, the oxygen concentrator, or any machine using that sensor?
Well, thank you very much, Titus, for your question. Right now, let me hand over to you, our engineers, to take those 3 questions.
All right, so I'll take the question from Good Luck. Can you hear me?
Yes.
All right, so the lifespan of an ultrasonic oxygen sensor used in a ventilator can depend on several factors, including the specific model, usage, and also what the manufacturer of the ventilator recommends. So typically, the manufacturer provides guidelines on the sensor replacement and the intervals, usually in the manual. So as a general guideline, ultrasonic oxygen sensors, they don't need calibration or replacement for up to 5 years. But then again, you need to check with what the manufacturer of the ventilator recommends on the replacement of the sensor. So I hope that answers your question. Good luck.
Yes, my network was bad. I could not get it. Please, can you repeat, please? My network was bad.
I'll just start all over again to answer your question. So the lifespan of an ultrasonic oxygen sensor used in a ventilator can vary depending on several factors. So the sensor model, the usage, and also what the manufacturer recommends. So typically, manufacturers provide guidelines on the sensor replacement and the intervals of use. This can come in the manual documentation that is coming with the ventilator when you purchase this ventilator. So in the event that you don't have the manual, of course, you should look for the source of the information on the ventilator and how you can do the sensor replacement as to how and when. So as a general guideline, you don't need to replace ultrasonic oxygen sensors in the period of up to 5 years. But then again, you need to see what the manufacturer says about this. So it's important to follow the guidelines of what the manufacturer recommends. I hope that answers your question. Good luck.
Okay. Will that apply to anesthetic machine and then ventilators?
So I want to give you another scenario whereby many of the oxygen sensors that we find in the ventilators and the anesthesia machines, they are electrochemical sensors and the paramagnetic sensors. So, and these sensors, they need to be looked on according to the requirements that the manufacturers have made. For example, there are other anesthesia machines that each and every time, every day, when you try to use them, when you want to administer the gases to the patient, they prompt you to calibrate them. You can do that daily, weekly, monthly, or annually. So this depends on the brand of the machine and also what the manufacturers actually indicated in the user manual. So it can depend. We can't give you a real exact answer on what is really done because we have different brands and different sensors in this used in these machines.
Yeah, thank you. Okay, yeah, sorry. In addition, sorry, please. If I know most times when you're on the ventilator, it does self-calibration, and sometimes when the sensor fails, can you still go on to use the machine? Can the machine gives you good results?
Sometimes when the calibration fails, it is hard for you to go ahead to use the machine, because sometimes, according to the manufacturers, they did it as a system that when you pass this test and the next one and the next one, and then you can use them. So that is why I am saying that it depends with the kind of devices. And also, if your machine has failed the calibration, but then you can go to the next step, this now will be something whereby you'll be skeptical about the readings or the results of the oxygen concentration or the gas concentration that you're giving to your patient, because you're not sure if your machine is well calibrated, recalibrated or not. So that would really be hard.
Okay.
Okay, thank you very much, engineers. I think because of time, we'll give you a detailed feedback, detailed answers to your questions after this call. So right now, can we handle the other two questions?
All right, so there was a question of the one who was asking the question saying, if there is a broken sensor inside the oxygen concentrator, can the concentrator give it? Can it display an error? Was that the question?
Yes.
All right. So usually when the sensor is broken, there is a leakage on the sensor. So when there is a leakage, the oxygen concentration cannot be generated to the recommended levels. So the concentrator usually gives an alarm because of the low oxygen concentration. So in this way, maybe you can know that the sensor is broken. Another way you can know that the sensor is broken is when you block the flow meter out, the outlet port. If the ball is not falling down properly, it means that there's a leakage somewhere. So it might be that the sensor is blocking. Yeah. So these are the main ways that you can know that the sensor is broken. Thank you.
Thank you very much for that. I hope it has answered the question. Can you take the other one? There's also another question on the chat. Zwange Ziambo Gondwe is saying, on innovations at GHII, specifically the oxygen analyzer, I have encountered this problem twice. The oxygen analyzer LCD just going blank after a period of 2 weeks without being in use. So with this issue, what's your recommendation for you being our manufacturer? I think we can also take that question.
Zwangi, can you come off mic and maybe answer if this was once when you placed it didn't come on, then when you placed again it did come on, or is it that the analyzer is still blank even to this date? Zwangi. All right, I'll go straight to answer your question. It's possible that you have. All right, okay, go ahead.
All right, thank you for this opportunity.
Yeah.
The first time I encountered this problem, fortunately, there was a team from GHII. So after I explained to them, they offered to carry it and they fixed it at your offices there. So that happened. But now the problem has come again, and up to now it's still blank. While when you open it, you find that when you switch on, the board shows that there is power, but the LCD part is the one that is not showing. But before that, a month ago, it was showing like flow rate, sometimes flow rate up to 998. So it's like, what's this a problem? So I thought like maybe there's moisture. Then I took it at light there. So after some time, I found it came back to normal. But now this problem of going blank is why I'm asking now.
All right. Okay. It's possible that there are broken parts inside, or the battery is dead. If you have you measured the voltage of the battery? Did you measure the voltage of the battery?
Yes, I measured the battery voltage and I found it 4.9.
All right. It's probably the battery. It should be around 9.5. Yeah, volts. So.
Oh.
Yeah. Thank you for giving us feedback. So where are you now?
At Zimbatecho.
All right. Okay. We'll get back to you, Zwanke, after this call.
All right. Okay.
Sure. Thank you.
Thank you very much. It's about 9 minutes after time, and I think I can just invite one more question if there is a burning issue somewhere, and then we close our session for today. If there is anyone out there.
Can I ask the question again?
Okay, go ahead.
For the electrochemical analyzer, how often do we calibrate?
So most often it depends on the usage. If you're using it on an anesthesia machine, it's recommended that you do calibration daily or after each and every use. Yeah. So depending on the use, whenever you want to calibrate the sensor, if you're using in the medical field where you just want to see the output of an oxygen concentrator or whatever source you want, it's actually recommended that you do the calibration on the spot. So I hope that answers your question.
Hello, yes, something just came. I forgot this question. Let me just ask, quickly.
Okay, go ahead.
Okay, and for the electrochemical analyzer, I think I did the calibration, the initial calibration for on an oxygen cylinder, and the result went beyond 100%. 102 or 3 or so. Is it normal?
That's actually not normal. You shouldn't get above 100%. So was this the time you were doing the calibration? You got over 100%?
Yes, over 100. Sometimes.
Right. All right. Okay. On the where you connect the pipe connecting to the electrochemical oxygen analyzer, there are 2 holes. Do you take note of those holes?
Yeah, the one we have in our office is just one port, just one hose direct to the oxygen cylinder.
I mean the electrochemical oxygen analyzer. You have a port where you connect a tube. The tube is connected to the port where you are measuring oxygen.
Yes.
So there is a hole actually on the neck where you connect this tube, which allows the oxygen to pass through, just to pass across the sensor. So when you close this hole, or when this hole is blocked, you get those unusual readings, which can show you up to 100% oxygen purity. Did you take note of the holes are blocked? All right, okay.
No, they're not
blocked. If the holes are blocked. All right, so when during the measurement, you are sure the holes were not blocked. So this issue most often happens when the holes are blocked. So whatever you're doing when measuring the oxygen, you should make sure that these holes are not blocked.
Okay.
Right. Yep.
Okay, thank you.
Thank you very much. I think we have taken enough for today. We apologize that we did not have enough time for this session, but if you have more questions or comments, I see there's another hand from Isaac Rabari. You can email us at info@oxygenalliance.org for more questions and also clarifications. And also you can go ahead and add a comment either on Facebook page or on YouTube, and we can as well address to that. But this marks the end of our call for today. Thanks a lot to you, our engineers from the Open O2. for your wonderful presentation and also taking our questions for today. It has been an educative session indeed, and we really appreciate having you on this talk. Thank you very much, our audience. You have been a very wonderful audience, and we expect to see you again on our upcoming course. Until next time, it's a goodbye.